So hi everyone. So in this class we are going to discuss some of the registers in 8086 processor. So last class we discussed memory segmentation. So in that memory segmentation we mentioned that these four segments are used to generate 20-bit physical address. So we know BIU generates 20-bit physical address. BIU means bus interface unit. This BIU contains four 16-bit special purpose registers called segment registers. So what are the four segment registers? We know already, last class we discussed. So they are code segment register, data segment register, extra segment register and stack segment register. CS, DS, ES and SS. So we'll see for code segment is used for addressing code segment where the program is stored. Data segment used to address data segment of the memory where the data is stored. Extra segment is used to address extra segment memory where the data is stored. Stack segment is used for addressing stack segment memory where the stack data is stored. So see here memory like that we are telling, right? So all these memories are external memories. The 20-bit external memory is there, no? In that external memory 4 segments will be there. Code segment, data segment, extra segment, stack segments will be there. To address these particular segments, this register is used. That's what we are telling. To address this code segment register is used. To address data segment register is used. To address extra segment register is used. To address stack segment register is used. So that much only we are understanding in this. We will see about this four registers, segment registers briefly in the upcoming slides. So before that, so here we will see like this segment registers actually used to generate 20-bit physical address, right? I told. So to generate 20-bit physical address, we need segment address and offset address. So for code segment, the segment address will be in this register. Offset address we will be getting from this instruction pointer. Similarly for data segment address will be in this data segment register and offset address will be getting from this source index register. For extra segment address will be in this extra segment register and offset address will be getting from this destination index register. For stack segment address will be in this stack segment register and offset address will be getting from one of this pointer register, either from stack pointer register or from base pointer register. So here we indicating this arrow marks. These registers are having offset addresses. This IP has offset address for code segment and this SP or BP has offset address for stack segment. SI is having offset address for data segment. DI is having offset address for extra segment. SI for data segment, DI for extra segment. So we'll see all these four segment registers briefly one by one. So first one, code segment register. So code segment register is of 16-bit long, and as I told you, CS contains the segment address, or we can say base address or start address of the current code segment, and IP contains offset address of the of the particular offset address is nothing but a distance, right? So distance from the base address to the instruction, whichever instruction we need to fetch. So how long the particular instruction's memory location from the base location, that is your offset, right? So that offset will be in this IP and base address will be in this CS, right? Next point, BIU generates or computes 20-bit physical address. This we already discussed. By logically shifting the contents of CS by 4 bits towards left hand side. So see this example I have given. How to generate physical address? We know the formula. What is the formula? Segment address into 10 plus offset address. This is the formula, right? So if suppose segment address is having 2000, if this segment address, which means CS, if it is having 2000, then that 2000 you are shifting, either you are multiplied with 10 or we can say shifting that 2000 by 4 bits towards left hand side. Then what it will become? 20,000. It will become 20,000. Am I right? So that is what they given here. Shifting the content of CS by 4 bits towards left hand side means nothing but this only. So content of segment is 2000, that you are going to multiply with 10 and then you are going to add with that 16-bit offset from IP. That is this one. So offset address also we need, right, to generate this physical address. So 4321. Here already 20,000 is there. Here 4321. Then it will become 24321. Right. This is your 20-bit physical address. So that is what given in this third point. And last point, all instructions of the program are relative to the contents of code segment register multiplied by 16 and then offset is added. So 16 they said, which means this they are representing in decimal actually, but here we are taking in hexadecimal. If you take in hexadecimal, then you need to write 10. In terms of decimal means here you need to take 16. That's it. So that is what they given in the last point. So I hope you understand this code segment. Code segment register means 16-bit register, and this code segment register contains base address and IP contains offset address. So by using the base address and offset address, we will be able to generate physical address, 20-bit physical address. So we can say base address or otherwise segment address or otherwise start address. So now we'll see the next one. So data segment register. So data segment register is also of 16-bit long and it points to the current data segment. Operands for most instructions are fetched from this segment. And 16-bit content of the SI or DI or 16-bit displacement are used as offset for computing the 20-bit physical address. So we can use SI or DI. I have given in the previous slide only SI. So remember SI, DI you can use, or other directly displacements also we can give, like 4321. Like that directly inside the square bracket you can use as a offset to generate this 20-bit, to compute this 20-bit physical address. Okay. So I hope you understand about this data segment register. We'll move on to the next segment register, that is stack segment register. So stack segment register is also of 16-bit long and it points to the current stack segment memory, right? And 20-bit physical address is calculated from the stack segment and stack pointer, and particularly this particular stack pointer will be used in push and pop instructions. So push and pop instructions. So first in last out, So based on that, this instruction, when we are discussing instruction set, that time we will discuss about this push and pop briefly. So remember that push and pop instructions, in that the stack pointers are mainly used, and stack pointer holds the offset address for stack segments, right? Again the same formula, segment address into 10 plus offset equal to physical address. The same formula we are using to calculate physical address for all the 4 segment registers to access the memory locations in the external memory. Okay. So in based addressing mode, 20-bit physical stack address is calculated from stack segment and base pointer. So base pointer also be used to calculate the 20-bit stack address, physical address, 20-bit physical stack, physical address for stack segment only in the based addressing mode. What is this based addressing mode? We will see in addressing mode concept, next concept. Okay. So we'll move on to the next register, that is extra segment register. So extra segment register of 16-bit long and points to the extra segment in which excess data like DS we are using to store the data, but in excess of 64 we can use this extra segment to store the data. And string instructions use this ES. So string instructions we discussed in instruction when we are discussing about which one, direction flag. That time we discussed string instruction is nothing but group of bytes. Group of bytes if you are accessing. So that time this direction flag also used. In that kind of instructions, this extra segments particularly we will use. Okay, and DI holds the offset and ES holds the segment address. So both will be used to generate the 20-bit physical address to reach the destination. Reach destination in the sense to access that memory location in the external 1 MB memory space, right? Total of 1 MB. Segment register wise, if you see, each segment registers of 64 KB memory. So all the 4 segment registers we discussed. First one is code segment register, next one is data segment register, next one is stack segment register, and last one is extra segment register. Next one is instruction pointer, IP. So this instruction pointer is also of 16-bit long, and this IP points the next instruction to be executed. So we know very well this IP holds the offset for code segment to access the code segment in the external memory. So IP will pointing the instruction which is going to be executed within that code segment. Okay, and it will get increment and decrement. Its content is automatically incremented as the execution of next instruction takes place. And register contains 16-bit offset address pointing to the next instruction code within the 64 kilobyte of the code segment area, right? So this IP is used to hold the 16-bit offset address for code segment, and this IP points the next instruction which is going to be executed within the segment, and it is automatically incremented, and it is pointing the next instruction which is going to be executed. So next we are going to discuss general purpose registers. 4 general purpose registers we have: AX, BX, CX and DX. So we'll see one by one all these 4 general purpose registers. These general purpose registers are in execution unit, but previously we discussed code segment register, data segment and extra segment, stack segment and IP. Those registers are in bus interface unit. These general purpose registers, whatever registers we are going to discuss in the upcoming slides, those registers are in execution unit. Okay, we'll see the first register, that is AX, that is nothing but accumulator register. So these accumulator register are of 16-bit long, but we can use this 16-bit register into two 8-bit registers like AL and AH. AL holds lower byte, AH can store higher byte of this AX register. So which can be combined together and used as a 16-bit register AX. So remember, AX can be used as two 8-bit registers AL and AH. AH hold higher byte, AL hold lower byte of total 16-bit value. AL in this case contains the lower order byte, that's what I said. AH contains the higher order byte. Then input output instructions use this AX, AL for inputting and outputting or inputting 16-bit or 18-bit data to the input port or from the output from the input output port, anything. So generally input output instructions are using this accumulator register for input as well as output of 8-bit or 16-bit data. Multiplication division instructions also using this AX, AL, AH and all, right. So when we are discussing when we are going to discuss about this addition, subtraction, multiplication, division, that time you will come to know how we are using this AX registers for taking the input or generating the output, like that. Okay, we will move on to the next register, that is base register. So here base register also 16-bit long, and in that the total 16-bit we can take it as two registers like we discussed in AX. The same way we can take here BL, BH. BL holds lower byte, BH holds higher byte. So BL contains lower byte of word and BH contains the higher byte of word. And this is the only general purpose register whose content can be used for addressing the 8086 memory. So based addressing modes we will use this BX register also. This BX register can hold the offset address. Okay, this BX address is used for addressing also. Okay, when we are going to discuss about addressing modes, that time we will come to know this based addressing modes. In that we will use this BX. So BX will give the offset to calculate the 20-bit physical address. So all memory references utilizing this register content for addressing use DS as a default segment register. Okay, so whenever BX is there, then DS will give the segment address and BX will give the offset address. Then by using segment address and offset address we can generate 20-bit physical address. Okay, next one is counter register, and in this also this counter register of 16-bit long is of 16-bit long, and this can be divided into two 8-bit registers like CL and CH, and CL hold lower byte and CH can store higher byte of this 16-bit value. So that is what here in the second point they given, and the instructions like shift, rotate, loop and all uses this CX. So CX can hold a value for counting. So like that and all we will use this CX register. So how many iterations need to be performed in that particular program? So for that and all we will use this CX. For example, that loop should continue 10 times, 16 times. So that count will be given in this CX. Next is data register. So this data register is also of 16-bit long, and we can represent into two 8-bit registers. We can divide that 16-bit register into two 8-bit registers like DL and DH. And DL can hold lower byte and DH can hold higher byte. Okay, that's what given in the second point. And third point, used to hold the high 16-bit result in that multiplication and division. Yes, particularly multiplication division, this data register will be used for the higher 16-bit values. Higher 16-bit values. Suppose 16 into 16 if you perform, it will come, final result will be more than 16 bits. So lower 16 bits will be reflected in AX, but higher 16 bit values, those values will use this data registers, will be reflected in this data registers. You can check this DX register, that higher 16 bit results will be reflected in this DX register. Similarly, in division also we will use 16 bit dividend when we are performing 32 divided by 16 like that, and 16-bit remainder after division. So for that remainder, showing remainder or higher 16-bit dividend, to show that we will use this data register to show that results. Okay. So when we are doing 13-bit multiplication division or 16-bit multiplication division, that time particularly multiplication and division in programs, you can see the result of higher 16-bit values. You can see, you can refer this DX register after AX. So now, so I have given, we discussed all these four general purpose registers. AX can be used as AH and AL. BX can be used as BH and BL. CX can be used as CH and CL. Similarly, DX can also be used as DH and DL. So if I use XXX, then it is 16-bit. If I use H, means it holds higher byte. If I use L, means then it holds lower byte. And this AH and AL are 8-bit registers. So all 16-bit general purpose registers can be represented with this two 8-bit registers. So kindly remember this. Whenever we are performing any task with 8-bit, that time we can use these 8-bit registers. Whenever we perform any operations with 16-bit values, that time we can use directly this 16-bit registers. So thank you. We'll see the remaining concepts in the upcoming classes.